I'm Dr. Sreedevi, Assistant Professor, IARE, Hyderabad. Today we are going to the session Graph Theory of Review of Basics 5. Today we will see what we are going to discuss in this lecture. We will be discussing walks, trails, paths, cycles, connected graphs, distance in a graph, vertices, cut edges, and some applications of weighting. We have roughly seen what a graph it is. Roughly, a graph is termed as a network of points connected with lines. And we have seen what is the formal definition of a graph. Graph G consists with two sets V and E, where the points of V are called vertices and the points of E are called edges. And how they are connected? The elements of E is given by E. For each element E of capital E is given as a ordered collection of distinct elements of V. Okay. And now we are going to see what a walk is. Given a graph, a walk in a graph is an alternating sequence of vertices and edges beginning and ending with vertices. Say W equal to V0, E1, V1, E2, V2, E3, etc. Vn minus 1, En, Vn, in which each edge is incident exactly with two vertices immediately preceding and following it. This is called a V0 Vn walk, or V0 Vn walk, like this is also termed as. Why we are calling it as a V0 Vn walk? Because the walk is starting with the vertex V0. Then it is going to V1 and ending with Vn. Now we have to understand that this walk consists of vertices starting from V0, V1, V2, etc. Continuously they are numbered. Also, it is called V0 Vn path, V0 Vn walk, and the edges are also E1, E2, etc. En. So there are n edges in it. Now we will be going to see much more things on this. The n vertices V0 and Vn are called initial and final vertices, or we can say that it is originating and terminating vertices of the walk. And all other vertices that are coming in between that V0 and Vn are termed as internal vertices. The number of edges occurring in the walk gives the length of the walk. So first, V0 is initial vertex, Vn final vertex. It is also termed, the initial vertex is also termed as originating vertex, and final vertex is also termed as terminating vertex. And the vertices that are coming in between, like that here, this V1, V2, etc. Vn minus 1 are called internal vertices. Okay, initial vertex, final vertex, and internal vertices. There are E1, E2, etc. En edges in this. So we call this walk to be our walk of length n. The walk is termed as closed if V0 equal to Vn. That is, if we are starting from a walk like that, vertex V0, we are going through this edge E1 to V1, then we are going through edge E2 to V2, etc. If it is like that, En and Vn, it will be that we are starting from V0, we are going to V1, then V2, etc. It's a normal walk starting with V0 and ending with Vn. If it turns to be like that, we are going through this and like that, En, then we are ending with V0 itself. Then we call it as a closed walk. Generally, for graph, in a simple graph, while giving a walk, we need not give the edges at all. The labeling of vertices itself gives the correct walk. Why it happens? Because in simple graphs, we don't have any loops, not multiple edges. So there is no confusion that if it is V1, V2, V3 and V4. This is a simple graph. This is a graph with multiple edges. And this is a graph with multiple edges and loop. This is pseudo graph. So if we are naming A, B, C, D, this E and F. I can start a walk from V1 to V4 in different ways. I can start from V1, A, V2, B, V3, D, V4, E, V4. It's also a walk. But if I don't have any this like this, here also I can start from V1, A, V2, C, V3, D, V4. Or I can have V1, A, V2, B, V3, D, V4. If I don't have anything like that, from V1 to V4, if I am going through V2 and V3, I can have only one path, V1, A, V2, C, V3, D, V4. Okay? There is no confusion of through which edge we have to cross through. From V2 to V3, I have only one edge. So there is no need to list the edges occurring in between them if we are considering only a simple graph. Okay? Now we are going to see different types of walk. We have seen that walk is just an alternating sequence of vertices and edges. Okay. Now if sometimes we may have some vertices repeating, sometimes we may have some edges repeating in our walk. If something is not repeating, and what we will call them. Okay. A walk in which all the edges are distinct is termed as a trail. That is, no edges repeat in that walk. Then it is termed to be a trail. If all the vertices of a walk are different, then it is termed as a path. A walk means an alternating sequence of vertices and edges starting and ending with a vertex. And if all the edges of a walk are different, it is termed to be a trail. If all the vertices of a walk are different, it is termed as a path. A graph which forms a path with n vertices is termed as Pn. Usually we are using this Pn in many situations in graph theory. That is a path with n vertices. A path with 5 vertices P5 is shown below. That is, we have 5 vertices U1, U2, U3, U4, U5. And this is that U1 to U2, U2, U3, U3, U4, U4, U5. It's a path with 5 vertices and it is termed as P5. A path or trail is closed if V not equal to V. We have already seen a walk is closed if the initial and terminal vertices happen to coincide. Same way, this particular path, that is in which edges do not repeat, it is termed as trail. And in which path in which the vertices do not repeat is termed as a path. Walk in which vertices do not repeat is termed as a walk. And if the trail and path happen to be closed, is termed to be closed if V not equal to Vn. That is, if initial and final vertices happen to be the same, then the particular trail or path is termed to be closed. A closed path containing at least one edge is termed as a cycle. So we have seen what a walk is, what a path is, and if a path is closed, it is termed to be a cycle. If a path contains a closed path contains at least one edge, then it is termed to be a cycle. The path V0, E1, V1, E2, etc., Vn minus 1, En, Vn is said to be a cycle if V0 equal to Vn. That is, the initial and final vertices happen to be the same or happen to coincide, then the path is termed to be a cycle. The path which forms a cycle with n vertices is termed as Cn. Just we have already seen a path with n vertices is termed as Pn. A path, if it is forming a cycle, and if it has n vertices, then it is termed as a Cn. Graph which forms a cycle with n vertices is termed as Cn. Any loop or pair of multiple edges also form a cycle. If n is even, then Cn is termed to be an even cycle. Else, that is, if n is odd, then Cn is termed to be an odd cycle. Here, see u1, u2, u3, u4. Here n is, and this is a closed path. A closed path is termed to be a cycle. And now see how many vertices are there? It consists of 4 vertices, so it is called. Usually cycle with n vertices is termed to be Cn, and here it is 4, and so we have marked as C4, and here it is C3. This is an even cycle, whereas this is an odd cycle. So I hope this walk, path, trail, cycle, all these things are okay. Walk is an alternating sequence of vertices and edges. A walk starts with a vertex and ends with a vertex. And the starting and ending vertices are termed to be initial and terminating vertices. All other vertices happening in between are called intermediate vertices or intermediate vertices. Then a walk in which all the edges are different is termed to be trail. A walk in which all the vertices happen to be different is termed to be a path. A closed path is termed to be a cycle. Look at this figure. Here we have vertices V1, V2, V3, V4, V5. Okay. Now see the first case V1, V2, V5, V2, V3. This is going from V1 to V. Here we are going from V1 to V2, V2 to V5, then V2 to V2, then V2 to V3. It's a walk. It's not a trail because we are repeating the same edge twice. That is V1, V2, V2, V5, V5, V2. That is, this edge is repeated twice. So it's not a trail. It's just a walk. Now consider this, which one? V1, V2, V5, V4, V2, V3. Now just repeat in it. So it's a trail, but the vertex V2 is repeating in it. It's not a path. And consider this one V1, V2, V3, V5, V4. V1, V2, V5, V4. It's a path. And what about this? V2, V4, V2, V4, V5, V2. V2, V4, V5, V2. It's a closed path. So it's called a cycle. Okay. Now consider this figure. If we have already seen the length of walk is termed to be as the number of edges occurring in it. Now consider this first figure. First case, we are starting from V0, going through B to V1. Then through D we are going to V2. Through G, V4. Then I, V4 itself. H, V3. F, V2. Then A, V0. Starting and ending the walk. This is a walk. Starting and ending in the same vertex. So it is a closed walk. Can it be termed as a trail or some path? No, because some edges have been repeated. And also the vertices have been repeated. So it's not a trail nor a path. Now consider this one. V1, E, V3, V1, E, V3, H, V4, again G, V2, D, V1. It's a closed path. So it's a cycle of length. How many edges occurring in it? 1, 2, 3, 4. 4 edges are occurring in this path, closed path. So we call it as a cycle of length 4. Consider this case. This third case one. V0, C, from V0 we are going to V3 through C, then H, V4, G, V2, F, V3, E, V1. What it is? It's a trail because cannot be a path because V3 has got repeated here. So it cannot be a path. But now edges has been repeated in this walk. So it is called a trail and length 5. Okay. So now considering this one V1E, V3 C, V0 A, V2 G, V4. It's a path. Is it a trail? Yeah, it's a trail also. Why? Because now edges has been repeated in it. So it is a path which is also a trail. Okay. Now we are going to give some definitions regarding the path, trail, and a grid of a graph is denoted by G, small g of G. This is the length of shortest cycle in the graph. The circumference, small c of G of a graph G, is the length of longest cycle. Grid means length of shortest cycle. So in this graph, what is the length of shortest cycle? It's 3. And what is the length of longest cycle? 1, 2, 3, 4. Okay. Is the length of longest cycle. Can we find any other cycle which is much more of length, longer than this 4? No, here. Here the shorter cycle is 3. We can start from here to go and here. Shorter cycle is of length 1. Sorry, not shorter cycle, not length 3 here. The shorter cycle is of length 1 here. Okay. So the grid of graph denoted by small g of G is the length of shortest cycle in the graph, and circumference c of G is the length of longest cycle. And now distance between two vertices U and V is the length of shortest path joining U and V, and denoted by d of UV. Distance between U and V. That is from when we are considering this V1, V2, V3, V4. From V1 to V4, I have two different paths, right? I can go from V4, go to V4 directly from V1, like that V1 to V4. And I also like this V1, V2, V3, V4. And shortest path means this is the distance between shortest path 1. Distance between, so V1 and V4 is 1. Else I can take this path also, V1, V2, V3, V4, so that it will be 1, 2, 3. But distance means the length of shortest path. It is 1. Now we will see something much more on distance. The shortest UV path of a graph is called geodesic of a graph. The diameter d of G of a connected graph is the length of longest geodesic. Longest UV path is called a diameter of the graph, and shortest UV path is found to be the geodesic. And this, consider this graph. Grid means length of shortest cycle. Shortest cycle from this graph is 3. And what about the circumference? Circumference is the length of longest cycle in the graph. Circumference is 4. And what is the connected diameter of a graph is the length of any longest geodesic. That is, longest geodesic here is 2. Connect any two vertices. We can find the maximum length to be 2. So the diameter is 2. Now we are going to see what is a connected and a disconnected graph. Now we have seen what is a graph and what is the formal definition of a graph. Then we have seen a walk in a graph, And what we have seen a trail, we have seen a path, cycle. Now we are going to see what is a disconnected graph and a connected graph. Okay. Two vertices of a graph are said to be connected if there exists a path joining them. What is path? Yeah, it's an alternating sequence of vertices and edges such that no two vertices repeating it. Okay, that is two vertices of a graph are said to be connected if there exists a path joining them. Suppose I am taking this vertex. I can go to any other vertex of this graph through any path. I can find a path between this vertex to any other vertex. Right? If I am taking this vertex V and this is U, I can go from V to U or U to V. There is a path existing between. I can go either this way or this way. Anyway, I can go to this from U to V and or U to V. Then we say that this graph is connected. That is, if any two pair of distinct vertices are connected by a path, then the graph is termed to be connected graph. As this graph is said to be disconnected. Or if we can find a path between any two pair of distinct vertices, we can say that the vertices are connected. And if we can find a path between any two pair of distinct vertices, that is, if every vertices of a graph are connected, then we say that the graph is also connected. Okay, else we say that the graph is disconnected. Consider this graph. If I am taking this vertex here, can I find a path to this vertex? Any of these vertices in this part? No. Cannot find any path to any of these vertices from here to here. I am unable to find. So this is a disconnected graph. A maximal connected subgraph of a graph is a component. Here we have two components. Here we have only one component. That is, maximal connected subgraph of a graph is called a component of a graph or a connected component of a graph. The number of connected components of a graph is denoted by omega g. Here omega g is 1, whereas here omega g is 2. Okay. Maximal connected subgraph of a graph is called a component. And here the number of components of a connected graph, number of components in a graph is denoted by omega g. Now here always comes across a question, how connected a graph is. How connected a graph means how many edges or vertices have to be removed in order to make a graph disconnected. For that concept, how to disconnect a graph, we are going to the terminologies of cut vertices and cut edges. A disconnecting set. Before going to cut vertices and cut edges, we will be seeing what is a disconnecting set in a graph. A disconnecting set in a connected graph is a set of edges or vertices whose removal makes the graph disconnected. From the name itself, it comes what is disconnecting set. If the particular things are removed or disconnected from the graph, we will get the graph disconnected. What is a disconnected graph? If we are unable to find a path between any two distinct pair of vertices in a graph, where the graph is termed to be a disconnected graph. Okay. Here the disconnecting set means the removal of particular set makes the graph disconnected. The particular set of vertices or particular set of edges makes the graph disconnected. Such graph set is termed to be disconnected set. Now consider this figure with vertices W, V, X, Y and Z and edges E1, E2, E3, E4, E5, E6, E7, E8. Now we will see what happens here. Vertex-wise disconnection. If I am removing these vertices W, X and Y, what will happen? The graph will be totally disconnected, right? I'm removing this one, this one, this one. When a vertex is are deleted means the edges which are incident with those vertices are also removed. So if I am removing this W, X and Y, all these edges E1, E5, E6, E3, E2, because every edge has at least one endpoint in these vertices. So every edges will be removed. And what is the resultant graph will be? W, X and Y is one removed. We will be left only with vertices V and Z. That is what shown in the first figure. When this first case W, X and Y is removed, we will be left only with this one. Okay? When W and X is removed, what will happen? W and X is removed means Y, Z and V will be there. But Y and Z are connected with an edge E4. So that edge will remain. Other edges, it's all incident with this X and W. So all other edges will be deleted and what remains is the vertex V. Okay, when the second case, this graph. And when third one, W and Y is removed. W and Y is removed means this much edges happening in will also be deleted. What we will be left with? We will be left with vertices V, X and Z, and so the edges incident on these three vertices E2 and E8 will be left. And that is the case of this one. W and Y, when W and Y is removed, it is shown here. Okay? When edge-wise disconnection happens, what is going on? When E1, E2 and E5 are removed, I will be removing this 3. Okay, then I will be getting this V in separate part. Then W, Y, Z and X. This will form another component and these other edges will be there. And W and X will not be connected. Okay, W and Y, this E3 will be there, E6, E7, E4 and E8 will be there. Baki, then these three edges will be removed and this vertex will be in another part and this will be called an isolated vertex and this graph will be considering us with two components with one isolated vertex. If I am considering this E3, E6, E7 and E8 are removed, what will happen? E3, E6, E7 and E8 are being removed. So that this one will be removed. This edge E7 and E8. What will be left with? These vertices W, V, X, Y and Z will be left. And which all edges will be there? E1, E5, E2 and E4 will be left. The second condition is shown here. That is when these four edges are removed, we will be left with this graph with two components like this. Okay? Disconnected graph with two components. A cut set is a disconnecting set. Now what we are going to define, what is a cut set? A cut set is a disconnecting set, no proper subset of which is a disconnecting set. That is a minimal disconnecting set. Okay? Here, what about this E1, E2, E5? Is it a minimal disconnecting set? No. Because even by the removal of this E1 and E2, we can disconnect this graph. This we will be a separate, we will be an isolated vertex and this thing will be another part. This by the removal of this E1 and E2 disconnects the graph. So this E1, E2, E5 is not a cut set. It's just a disconnecting set. A cut set is this E1 and E2. When this considering these edges. Okay. What about this E3, E6, E7, E8? Can any subset of that set disconnect the graph? No. So it is a cut set. Okay, a graph may have different cut sets of vertices and cut sets of edges. Similarly, what about this W, X and Y? It's not a cut set. Why? It's a disconnecting set, but WX itself is required to disconnect this graph into two components. So WX is a cut set, WY is a cut set, whereas WXY is a disconnecting set but not a cut set. So this cut set and disconnecting set, minimal disconnecting set is termed to be a cut set, or a cut set is a disconnecting set such that no proper subset of this a disconnecting set. Okay. If a graph is a connected graph, which is not complete, the vertex connectivity is denoted by kappa g, is the size of smallest separating set or disconnecting set in G. What is vertex connectivity is the smaller, that is the least number of vertices whose removal makes the graph disconnected. Okay. In the figure, if you are removing this graph, two vertices can make the graph disconnected. Right? So, in this figure, the kappa g or this vertex connectivity of graph is 2. And G is also called K connected if kappa G is greater than or equal to K. That is, here we have kappa G equal to 2. So, it is K connected, it is 1 connected. By the removal of one vertex, it can be this K 1 connected, and it is also 2 connected because the vertex connectivity of graph is 2. What is the vertex connectivity? It is the minimum number of vertices whose removal makes the graph disconnected. Or vertex connectivity is the smaller size of separating set in a graph G. Can be termed in different ways. That is, basically we have to take in mind that vertex connectivity of a graph is termed to be the minimum number of vertices whose removal makes the graph disconnected. Here it is kappa G equal to 2. Similarly, edge connectivity is termed as minimum number of edges whose removal makes the graph disconnected, and it is the edge connectivity, and it is denoted by lambda g. Vertex connectivity and edge connectivity. Vertex connectivity, minimum number of vertices whose removal makes the graph disconnected, whereas edge connectivity is the minimum number of vertices whose removal makes the graph disconnected. Here, how many vertices, a minimum number of vertices we require to make this graph disconnected? These two edges we can remove and we can make this graph disconnected. So, here also, earlier as K connected, we called it if lambda K edge connected if lambda G is greater than or equal to K. So, here we have 2. So, we can say that this graph is 1 connected, and also we can call this graph is 2 connected. We cannot say it to be 3 connected or so. The vertex connectivity, edge connectivity. Now we are saying what is the bond of a graph. The minimal non-empty edge cut of G is called a bond of G. Non-empty, what is minimal non-empty edge cut is called bond. Here the bond is 2. Now we will see what is a cut vertex and a cut edge, or a bridge or an articulation point. A vertex V of a connected graph G is called a cut vertex or an articulation point if the removal of that vertex makes the graph disconnected. That is, we know the number of connected components of a graph is denoted by omega G. If omega of G minus that V is greater than 1, then we say that V is termed to be a cut vertex or an interpolation point. Consider this graph, first graph. Here if we are removing this vertex, nothing will be happening. The graph will be with one component itself. Same thing here if we are removing it, no, nothing, no. Only we will be getting this, we will get this component like this attached with this component. But if we are removing this vertex, V, the graph will be totally disconnected. And this V is called this articulation point or cut vertex. A graph may have different number of cut vertices and different number of cut edges. But here, this one, only one cut vertex. And this is called this articulation point of a graph. That is whose removal makes the graph totally disconnected. Okay? And what about this? If we are removing any of these edges in this graph, other than this, the graph will not get disconnected. And if you are removing this E, you will get one component like this and another component like this. So, this E is termed to be a bridge or cut edge. So, what is this? Articulation point or a cut vertex, a bridge or a cut edge. Okay? Now, the blocks in a graph G. A non-separable graph is before seeing what is a block, we will see what is a non-separable graph. Non-separable graph is a connected, non-trivial graph, but has no cut vertices. That means it has no cut vertices, it is non-trivial, and it is a connected. This is a block of a graph. Okay. Even if I remove this vertex, the graph will be connected and all. What about removing these vertices? It is also a connected graph. But if I am removing these, and if removing these two vertices, it is also a connected graph. It is a connected, and if removing these three vertices, this becomes disconnected graph. But what the resultant graph is? A trivial graph. So, a non-trivial this non-separable graph is a connected non-trivial graph and has no cut vertices. Here, like this, it is a block. Block is the maximal non-separable subgraph, which cannot be, again, which we cannot disconnect or we cannot divide it into a subgraph. So, block is a maximal non-separable subgraph. This is block. Okay. First, we have seen what is non-separable graph, and now we are seeing what is a block. If G is non-separable, and it is often termed to be a block. Here, in this graph, it is non-separable here. So, this itself is termed to be a block. Whereas, here we can separate it into different parts. I can keep this one part, keep this one part, and keep this edge another part, and this portion another part. So these are 4 different blocks of that G. Okay. This portion, first portion, if I am taking this, and I can take this edge to be this one, second block. This third block and fourth block. So, these are connected non-separable subgraphs. These are called blocks. And now we will see what is this we have seen what is a connected graph, disconnected graph, a disconnecting set, then cut vertex, cut edge, vertex connectivity, edge connectivity. Now we will see this Lange's theorem. Let G be a connected graph and U and V be 2 vertices of G. A set of edges of G is said to separate U from V if the removal of these edges destroy all UV paths. Now we will see what is Menger's theorem. Now we have already discussed what it is a path, what is a walk, what is a path, what is a trail, then what we have seen, what is this disconnecting sets, then cut set, cut vertices, vertex connectivity, edge connectivity, and so on. And we have seen these blocks also. Now we will see what is this, what says that this Menger's theorem. It's all about the connectivity of a graph. Let G be a connected graph and U and V be two vertices of G. Okay, a set of edges of G is said to separate U from V if the removal of the set of edges destroy all UV paths. That is that we have a path somewhere U and V. If we are removing all these paths between UV, then the set of edges are said to separate U and V from this. And logically, the set of vertices are said to separate U and V if we can find the removal of these vertices disconnects all the UV paths. Then we can see that is edge separating and vertex separates. If the removal of certain edges separates the UV paths between all certain edges separates the UV paths in a graph G, then these edges are said to separate U and V. Similarly, if the removal of some vertices, certain vertices, say ABC, if we are removing this ABC in the UV path, and then the UV path is destroyed, then we say that these vertices A, B, C are said to separate U and V. And we will see how this Menger's theorem has two forms, edge form and vertex form. Let's see this edge form. Let G be an arbitrary connected graph and U and V be two vertices of G. The maximum number of edge disjoint UV paths is equal to the minimum number of edges separating U from V. That is, the maximum number of UV paths is the minimum number of minimum edge connectivity of U and V. Okay. Then the Menger's theorem of vertex form. For arbitrary connected graph G, the maximum number of vertex disjoint UV paths is equal to the minimum number of vertices that separates U from V, where U and V are non-adjacent vertices of G. If U and V, that means if U and V are any two non-adjacent. Now, what does that mean by non-adjacent? Because U and V are not directly connected by an edge, then they are said to be a non-adjacent vertices. So, if we are able to the maximum number of vertex disjoint UV paths is equal to the minimum number of vertices that separates U from V. Okay. So, combining this Menger's form of vertex form and edge form, we will get that in a finite graph, the size of minimum cut set is equal to the maximum number of disjoint paths that can be found between any pair of vertices. There we have seen that if U and V are distinct, we are distinct vertices which are non-adjacent, then we can find the maximum number of edge disjoint paths is equal to the minimum number of vertices that separate U from V. And here we have these are connected. If G is a connected graph and U and V are two different vertices, then the maximum number of edge disjoint paths is equal to the minimum number of edges separating U and V. And combining these two, we get in a finite graph G, the size of maximum cut set is equal to the maximum number of disjoint paths that can be found between any pair of vertices. Okay, that is the minimum cut set is equal to the maximum number of disjoint paths, or number of disjoint paths is equal to the minimum cut sets between these two particular vertices. Menger's theorem characterizes the connectivity of a given graph. Okay, we have to find the minimum cut set so that we can find the maximum number of disjoint paths. So the Menger's theorem characterizes the connectivity of a given graph. Now we will see some applications of these graphs. before going to the application, we will see what is a weighted graph. Okay. Weighted graph is a graph in which each edge is assigned a positive number. Say W of E, called the weight of edge. Suppose if there are V1, V2, V3, this V6, and they are connected like this with the edges. And if I am assigning a positive real number to this each edge, that positive real number is termed to be the weight of that edge, and it is denoted by W of E. And weight of graph, this weight of edge is given like that, W of E. And weight of graph, W of G, is the sum of weights. That is, if G is of order P and size Q. We have, that is, Q edges are there. And each edge is assigned a positive real number called the weight of that edge. And if the weight of graph is the sum of all the sum of the weights of particular edges, that is W of E1 plus W of E2 plus etc. plus W of EQ, where E1, E2, etc. EQ belongs to the edge set of G. Okay. And what is the weight of this graph? What is the weight of this edge? Connecting this, what is the weight of this edge? It is 18. And what is the edge of this weight? It is 28. And what is the, so this graph has not 6 vertices, 7 vertices. I forgot to put this one, 7. Okay. And what is the weight of edge connecting V7 and V3? No edges that we will be putting. Either we can put the 0. Here we have weight to be 14. Okay. So what is the total weight of this graph? We can take it to be 28 plus 14 plus 16 plus 12 plus 18 plus 24 plus 22 plus 25 plus 10. Okay. Then application of weighted graphs. Weighted graphs has a much more application in graph theory. Where actually when we have seen this in shortest path problem, to find the shortest path problems and all, we are using weighted graphs. Weighted graphs are used in the application where we need to take into account of some cost or measurement between vertices of graph. For example, weights can represent the time taken or traveling expense or distance from one location to another. Can be between the places and all. The weights can be anything like that. Vertices can be places and anything. Suppose a problem. Consider this problem. Suppose we have a map like this, from connected with A to L. Suppose the places are named from A, B, C, etc. to L. Okay. If the lengths of roads are marked in these edges, that is, every edge has been assigned a weight. That is, it is a weighted graph. If the length of roads are marked, what is the length of shortest path from A to L? We have to find the shortest path. But also it can be the measurement of paths, or it can also be the traveling time or traveling cost. So we have to find these things from A to L. The upper bound can be easily calculated from taking any path from A to L. So if I am taking A, B, D, G, A, B, D, G, J, L, I could find that the upper bound is 80. So the length of shortest path should be less than 80. How we can find? The mathematical way to approach this problem is move from left to right of the figure. Okay, from left to right of the figure. We have to assign each vertex V L of V, indicating the shortest distance from A to B. That is, if we are approaching this vertex K, then we can have L of K to be either L of H plus 6 or L of F plus L of I plus 2, whichever is smaller. That is, we are assigning a number L of V to each vertex whose distance is shortest from the originating vertex. Say here we are taking, if it is to be A, we have to find this A to that vertex. Okay. Applying this algorithm, we first apply label 0 to vertex A. Then we can find give vertices B. What are the vertices adjacent to A? You can see that there are E, B, E and C. What is this? L of B can be given, L of D is can be given as L of A plus 3. Then L of A plus 9 and L of A plus 2. Okay, this L of A we have given as a 0 to A, and so this 0 plus 3, so it is 3, here 0 plus 9, 9, and here it is 0 plus 2, 2. And so this we get the smallest weight. Smallest value is at C. So we fix L of C to 2. Now assign the look at the vertices adjacent to C. And assign F at which one is here? It is F, E. Any other vertices adjacent to C? No, we then assign temporary labels to F. L of this 2 plus 2 plus 9, 11, and this 2 plus 6, 8. So first we got L of E to be here 9. So now we got it to be 8. So now we have to reconsider this. And this, so L of this temporary label has been this what lower this temporary label of E to be 8. Then now the smallest temporary label in this level is at B. So fix it to be B at 3 permanently. Now we can, what is the neighbors of B? B, it is D. Here it is D and E. Okay. Then we can see that what is this E? We have here 3 plus 4, 7. Here 3 plus 2, 5. So this L of D can be here. Earlier we had it to be 9. Then it got to be at label at E got to be 8. Then now we have got the label at E to be 7. Now we are fixing the label at E to be 7 and label at B to be 5. Sorry, label at D to be 5. Okay. At this level, this out of 5 and 7, label at D is less. So we consider this label at D. And now what is label at D is fixed 5, and we get this label of G. Then label of G to be at 8, and then we get label of H to be 9. From here we get the label of F, I, K, and N. And we get this label of L to be 17. And that we following from A to B, B to E, E to F, E to H, H to F, F to I, then K, then L. Okay. Which implies the shortest path from A to L is 17. So which implies the shortest path from A to L is 17. So this it is the application of weighted graph. That is, we will be going through the least edges with least weight to the and advancing at each level in a particular format like this. We will be going this step-by-step process. And this is the process of finding the shortest path. Okay. Now we will see what we have discussed or totally in this session. We have seen what is a walk. Then we have seen what is trail, path, and cycles. Thus, trail, path, and cycles are different conditions when happens in a walk. If no edges occurs again in a walk, then it is termed to be a trail. And if no vertex again appears again in twice in a walk, it is called a path, and closed path is called a cycle. Then we have seen what is connectedness and disconnectedness of a graph. If we can find a path between any pair of distinct vertices, then we call those vertices to be connected. And if every pair of vertices in a graph are connected, then we term the graph to be a connected graph. Then we have seen what is a cut vertex and a cut edge. If the removal of a vertex disconnects the graph, then we call that vertex a cut vertex. And similarly, if a removal of an edge disconnects the graph, then we call that a cut edge. Then what we have seen, the blocks and connectivity. Blocks means minimal, non-separable component of a graph. Then we have seen what is a weighted graph, and we have seen a shortest one application of weighted graph, that is shortest path problem. Some other applications of weighted graphs we will discuss in next sessions. Okay, thank you for watching this video. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.